Now, what is the loading arrangement on continuous beam? That we could get the maximum support moment and maximum span moment. As per the IS 456-2000 version, clause number 22.4.1, and is available on page number 35. I have that clause. What exactly the clause is? What exactly the clause is? That means if you put the load combination on continuous beam, at which loading arrangement you get the maximum negative moment, that means maximum support moment and maximum span moment, that criteria is given in IS code on page number 35. So I will read it. First one, design dead load on all spans with full design imposed load on two adjacent spans. Okay, I will tell the meaning of this sentence by drawing one diagram. Okay, so this is the continuous beam. This is the continuous beam. Okay, this is the continuous beam. Okay, so this is support A, support B, support C, support D, support E. So when you apply the maximum design load on adjacent span, that means when you apply the maximum design load on adjacent span, and all other spans having minimum load, and all other span having minimum load, that means this is W minimum. W minimum means this is only dead load. Okay, and W maximum means you have to consider dead load plus live load with factor. That means the maximum load is applied on adjacent spans, then we get the maximum negative moment. Then we get the maximum negative moment. On this support. On support B. Okay. Maximum negative moment means maximum support moment. Maximum negative moment means maximum support moment. Okay, is it clear? Now, what is the second criteria? If you apply the design load on alternate spans, so I will tell you. Okay, if you apply this design load, suppose this is support A, support B, C, D and E. If you apply this design load on alternate spans, I want to take the chalk. Okay, alternate span, that means span AB, alternate span CD, like this, and all other spans having a minimum load, Okay, so this is W minimum, means only dead load. This is W maximum, means you have to consider the combination of a dead load and live load, and we have to multiply the factor. You have to multiply by the partial safety factor. In this condition, in this loading arrangement, you get the maximum positive moment in span AB and in span CD. So we get the maximum positive moment. That means span moment. That means span moment in span AB and CD. In span AB and CD. AB and CD. Okay. So if we arrange the maximum load on adjacent span, on this support we get the maximum negative moment. And if we arrange the maximum loading on alternate spans, you get the maximum positive bending moment on span AB and CD. So this is the criteria of loading arrangement on continuous beam. Now I want to move towards the next part, next theoretical part of this unit is redistribution of moment. I will explain it. What is exactly the redistribution of moment? What is the need of redistribution of a moment? What are the advantages of redistribution of a moment? And what is exactly the meaning of redistribution of moment? I will tell you considering as per the IS 456 2000 version, redistribution of moment. Okay, I will write it. Redistribution of moment. Redistribution of moment. The heading itself giving a meaning of this term. Redistribution of moment means distribution of load, distribution of a moment from one point to another point, from one point to another point. The simple definition is distribution of distribution of load, or you can say moment. Distribution of load from old plastic hinge. I will tell you exactly how it is old plastic hinge and new plastic hinge. Distribution of load moment from old plastic hinge to newly developed the plastic hinge. Newly developed plastic hinge is called redistribution. Is called redistribution of load or moment. The simple meaning is distribution of load from one point to another point, one plastic hinge to another plastic hinge is nothing but the redistribution of moment. So I will exactly tell you the meaning of this definition by giving one simple example of fixed beam. Okay. First, I want to draw a diagram. Consider a fixed beam. Okay. Consider a fixed beam, because we know that the fixed beam is the indeterminate structure with static indeterminacy is 2. Okay. And when we apply the load on the fixed beam, let it be W1, the beam wants to bend under its elastic limit, up to its elastic limit, like this. Beam wants to bend like this. So this is the bending behavior of a beam. This is the bending behavior of a beam under the applied load up to the elastic limit. Before failure, Okay. Now what is the bending moment diagram? So what is the bending moment diagram of the fixed beam? I am telling you how the redistribution of moment is going on. Now I am going to tell you how the redistribution of moment is going on. Okay. So the bending moment diagram is like this. So maximum bending is developed, bending moment is developed on support, obviously. Okay. And at center, the span moment is developed. So this is the support moment and this is the span moment. Now if you want to join it, the bending moment diagram is like this. Bending moment diagram is like this. So this is the support moment. This is support moment. This is the support moment. Okay. And this is the span moment. This is the span moment. It is the next span moment. Span moment. Okay. So this is the bending moment diagram of this fixed beam. Now, if you increase the load on fixed beam, now I want to draw another diagram here. If you increase the load on fixed beam, okay, W2, now beam is want to fail by developing the cracks. Simply, that cracks are called plastic hinges. By developing the plastic hinges where the peak bending moment is developed. Okay. So the beam wants to bend like this. Look here. Beam wants to bend like this after the elastic limit of the material. Okay. And how it fails? First it develops the crack at this joint. First it develops the cracks at these joints. That means it develops the plastic hinge. Plastic hinge. Okay. And because the maximum bending moment is developed at this location due to fixity, so at that location the first plastic hinge is developed, and after that the another plastic hinge is developed at the center of the beam, at the center of the span. Okay. So first this plastic hinge is developed, and after that this plastic hinge is developed. First cracks developed at this location, after that the cracks developed at this location, and failure is done. Failure is completed. So in between that, when this plastic hinge is developed, it is an old plastic hinge. And this is the newly developed plastic hinge. So before failure, what exactly the fixed beam behave? That means at this failure, at this joint, the before failure, it transfers the load to this newly formed hinge. And then it fails. And after that, this joint fails. And finally the failure of a fixed beam is done. Failure of fixed beam is complete. Now in between that, while transferring this load on this hinge, it reduces the bending moment at this location and increases the bending moment at this location, obviously, because this load is transferred on this hinge. So what exactly the bending moment diagram will compare to this? At this location, so this is the baseline. Okay, the support moment reduces. if we consider the level of this previous diagram, the bending moment on support is reduced because the load is transferred on this hinge, and simultaneously due to increase on the load at this location, the bending moment on span is increases. Just a minute. So, if we compare the bending moment diagram with this diagram, at this location the support moment is reduced. Simultaneously, at this location the span moment is increases. The bending moment diagram is like this. That means it is a reduction of bending moment, and this is the increment of bending moment. So this is the reduction of bending moment and increase of bending moment. This is called the redistribution of moment. Reduction at peak point, simultaneously increase in another point. It is nothing but the redistribution of moment due to distribution of a load from one plastic hinge to another plastic hinge. So what about the IS code? Want to say related to the redistribution of moment? What are the points that we have to consider? That is, as per the IS code, okay, first point, as per the IS 456-2000 version, maximum 30% redistribution of moment. Maximum 30% redistribution of moment is allowed. As per the IS code, maximum 30% redistribution moment is allowed. Second point is, due to reduction in bending moment. Okay, so due to reduction in bending moment at peak point. Obviously there is a reduction in steel conjunction at that point. Okay, due to reduction in bending moment at peak point, it reduces conjunction. Conjunction of steel at that point, peak point. So this is the second point. If you want to write down some theoretical part, you have to write down all these things. Okay. So if we reduces the bending moment at peak point, that means on support, obviously it reduces the conjunction of a steel at that point. Next is, due to maximum percentage increase. Okay, due to maximum percentage increase increase of redistribution. Okay. Due to maximum percentage increase of redistribution, due to maximum percentage increase of redistribution, it reduces the depth of neutral axis of beam. It reduces the depth of neutral axis. Depth of neutral axis of beam, and if the depth of neutral axis is reduces, the behavior of a beam is under reinforced behavior. It reduces the depth of neutral axis of beam, and by reduction of depth of neutral axis, beam will fail. Of beam, the failure of beam, the failure of beam as under reinforced section, So what is the point 3? Due to maximum percentage increase of redistribution of moment, if you increase the percentage redistribution of a moment, it reduces the depth of the neutral axis of beam. Then the failure of beam as acting as under reinforced section, and if the beam is acting as under reinforced section, so it is very easy to design. It is very easy to design. Okay. Last one. If the redistribution the moment along length of member, if the redistribution of a moment along length of member is uniform, redistribution of moment along length of member is uniform, then the section becomes economical section. Then the section become a economical section. Okay. Redistribution moment is uniform due to redistribution of moment along the length of beam is uniform. Okay. Then section become economical. Then section become economical. So these are the points you have to consider under the redistribution of moment, under the redistribution of a